is connected, and this pulley is moving upwards with acceleration a, and suppose the acceleration of this block is b. So now we want to find out the relationship between the accelerations a and b, that is the acceleration of pulley and the acceleration of block. So let's take this ground as the reference point. So let's say that the length of this part of the thread is x, and the displacement of the block with respect to this reference point is y. So the total length of pulley will be L is equal to x plus this length, and this length is nothing but x minus y. So total length will be x plus x minus y, or it is equal to 2x minus y. So now what we can do is we can double differentiate this length. Since L is constant, its differential will be 0. So differentiating it twice will get 0 is equal to 2 into d square x by d2 square plus minus d square y by dt square. Now y is the displacement of this block with respect to this reference point. So the double differential of y will give the acceleration b, that is how fast the block is moving away from this reference point. Similarly, the displacement of the pulley with respect to this reference point is x, so the double differential of this displacement will give the acceleration of the pulley with respect to this reference point. So we can write d square x by dt square as a, that is acceleration of pulley, and d square y by dt square as b, that is acceleration of the block. So we have 0 is equal to 2a minus b, or b is equal to 2a. So the acceleration of block is twice of the acceleration of pulley. Now let's see one more solved example. In this example, a force F is applied on the object of mass m as shown in the figure. We'll see the figure in a few moments, and we need to calculate the acceleration of mass small m. Now let's see the figure. So in this figure, a force F has been applied to the block of mass m, capital M, and we need to find out the acceleration of block of mass small m. Now let's see what are the various forces which are acting on these three blocks. So first we'll assume that the acceleration of block of mass capital M is a, and the acceleration of the block of mass small m is c, and the acceleration of block of mass m dash is b. So as you can see from here, the tension in the thread is T, and since it is a single thread, so the tension will remain throughout the same. So the forces acting on the block of mass m dash is tension T, T, T and T. So the total force which is acting on block of mass m dash is 4T. Similarly, the tension force acting on the block of mass small m is T, and the force acting on the block of mass capital M is 2T. So now we can write the equation of motion of for these three blocks. So let's find out the equation of motion for the three blocks. So first we'll take the small block of mass small m. So the net force on this block was T, and its acceleration was c. So for this block the equation of motion would be T is equal to minus mc, because the direction of acceleration and the force applied is opposite, so we have included a minus sign here. Similarly, for the block of mass capital M, the net force was F and 2t, and its acceleration was a, so we can write F minus 2t is equal to capital M into a. And for the block of mass capital M dash, the net force acting on it was 4t and its acceleration was b, so we can write 4t is equal to minus m dash b. Here again the direction of net force and the acceleration are opposite to each other, so we have added a minus sign here. So these are the three equations of motion. Now let's find out how can we use the thread constraint. Now as you can see here that the total thread length is, this is y, so this will again be y, this is also y, and this is also y, this is x, so this will again be x. So the total thread length L is 4y plus 2x plus z. Now if we double differentiate this equation, we will get 0 is equal to 4 into d square y by dt square plus 2d square x by dt square plus d square z by dt square. Now you can write 0 is equal to, now d square y by dt square is nothing but b, so 0 is equal to 4b plus d square x by dt square is nothing but a plus 2a, and d square z by dt square is nothing but c. So this is the relationship between the acceleration of these three blocks, that is 4b plus 2a plus c is equal to 0. So we'll keep in mind this thread constraint. Now we have these equations, that is 4b plus 2a plus c is equal to 0. Now if you recall that the force acting on the block of mass small m was t and its acceleration was c, the net force acting on the block of mass capital M was F minus 2t and its acceleration was a, and the net force acting on the block of mass M dash was 4t and its acceleration was b. So here we had the various equation of motions as t is equal to minus mc, f minus 2t is equal to ma, and 4t is equal to minus m dash b. So these are the three equations. Now from equation 1 the value of c will be t by minus m. Similarly from equation 2 the value of a will be f minus 2t by capital M, and from equation 3 the value of b would be 4t by minus m dash. So we can put the value of a, b and c in this equation, that is the equation which we derived from the thread constraint. So we can write 4 into b, that is 4t by minus m dash, plus 2 into a, that is f minus 2t by m, plus c, which is t by minus m, is equal to 0. Now from this equation we can get the value of tension, that is T, in terms of capital M m dash and m. So this is straightforward. We can get the value of t from this equation. This is equation 4. Now once we get the value of equation t, we can find out the acceleration of a block of mass small m, which is c, and c is given by t by minus m. We already have the value of t from this equation, that is equation 4. Now we can also get the value of c, which is the acceleration of the block of mass small m. Now we'll see how we can solve some pulley system using U-axis theorem. In this theorem, we consider the thread tension as an internal force of the system, and the axis of motion is taken along the thread. So for example, here we have a pulley system, the most basic pulley system. So as you can see that the axis of motion is taken along the thread, that is like this. So this is our thread, and at the two end of thread we have blocks of mass m1 and m2. So now in this system the tension T will become an internal force. So the net force acting on the system is m1g, which is weight of the block mass m1, and m2g, which is the weight of the block of mass m2. So if we suppose that the acceleration, the block m1 is coming down, so it means that this is the direction of acceleration a. So we can write the equation of motion m1g minus m2z, this is the net force. This should be equal to m1 plus m2a, because this is the total mass of the system and this is the acceleration of the system. So from here we can get a is equal to m1 minus m2g by m1 plus m2. So this is the acceleration of system. So this is the acceleration with which the block of mass m1 will come down and the block of mass m2 will go up. Now if we take the block of mass m1 alone, so on this block the net force is m1g minus t, and the acceleration of this block is a. So we can write m1g minus t is equal to m1a, or t is equal to m1g minus a. Now we can substitute the value of a from here, so we can get the value of t as well. Now we'll see what is pseudo force. When an object is viewed by an observer from a frame of reference which is accelerating, the object seems to be accelerated in opposite direction with the same magnitude of acceleration. Therefore, to justify the acceleration of the object for an observer in the non-inertial frame, a force is assumed to be acting on the object which is responsible for this acceleration. According to Newton's law, this force must be equal to the product of the mass of the object and the magnitude of the acceleration of the frame, and the direction of this force should be the direction of pseudo acceleration of the object. So for example, suppose